looking at this conservation of energy. So we're looking at how the energy changes in different situations. One of the things that you will see in your book especially is a big long equation that says the kinetic energy before plus the potential energy before is equal to the potential energy at the end and the kinetic energy at the end and the work being done. It's a great big long equation, and sometimes that just gets really confusing as to what it is that we're actually looking at. One way that we can help visualize this conservation of energy is what we call an energy bar chart. And these are just a before and after picture of the energies associated with a system. Basically, they're little semi-qualitative bar graphs is what they look like. And so let's start with a fairly simple situation. We're going to have a ball. We have a wall here with a ball on the top. And this ball is going to fall off. Okay, and it's going to go down and it's going to hit the ground. Okay, and what we want to look at is how does this energy change from this point to this point. Okay, so we're looking at that change in energy, that conservation of energy. And we have the ball sitting up here on the top. Up here on the top, the ball is not moving. Okay, but then we kind of roll it off, and because of gravity, it's going to fall down. So the first thing that we want to do is define our system. Okay, so when we say the system, what are the things that we're talking about? So when we say the energy, this conservation of energy, what energy are we talking about? Are we talking about the wall? Well, the wall doesn't change, so that's not very helpful. But we have our ball over here, and that's kind of what we're interested in. So we've got our ball. And just like we did with our forces, we can identify anything that's interacting with that ball. Okay? So in this case, the wall doesn't really do anything to it, it just kind of holds it up. So we could say that it's interacting with it, but it doesn't change anything about the ball. So in this case, what we want to do is what changes the energy of the ball. And in this case, what we have is the Earth over here, okay, with its force of gravity pulling the ball down. Once we roll that ball off of the wall, the Earth is going to pull it down with that force of gravity. So our system would include the ball and the Earth. Now what we're going to do is we're going to come over here and draw a little circle, maybe. All right, so we're going to draw a circle, and this is going to represent our system. This is just what we're talking about. So our ball and our Earth are a part of our system. So that's what we're looking at. For our initial conditions, we want to identify what energies are associated with the ball. So this here is our initial condition. I'll just write that out. Okay, this is our initial condition right here. So over here on the left, what we're going to do is we're going to draw just a little bar graph, really is all it is, that's going to show us kind of a semi-quantitative, qualitative description of those energies. Right now we have kind of three main energies that we've talked about that a substance can have, an object can have. We have kinetic energy, right? That's one thing that could be happening. We have potential energy in the form of gravitational potential energy. And then we also have potential energy in the form of an elastic substance or a spring potential energy. So our ball is sitting up here on top of our wall, and it's not moving, it's just sitting there. So it doesn't have any kinetic energy. And there's no spring involved, so there's no potential spring energy. There is, however, some gravitational potential energy. Okay, so down here we have y equals 0. This is our ground or our table or whatever it is. We can define this as 0. And so our ball is some height above that 0. So we do have some gravitational potential energy. So on our chart, we're just going to draw just a little bar graph is all this is. So we're just going to draw some bars in here. Say 5. Okay, it doesn't really matter. We're just going to show how that energy is changing. So in our initial conditions, all of our energy is represented by that gravitational potential energy. But then the ball falls. So this right here is our final situation. Okay. Now we could talk about the point where the ball actually hits the ground, or we could talk about that point just right before. If the ball hits the ground, we're going to have some other things that kind of need to be taken into account. So we are going to say that this is that split second right before that ball hits the ground. It really can't fall any farther, and it's still moving, but it hasn't quite touched the ground yet. That's going to save us some work. All right, now we're going to draw another little bar graph over here on the other side to represent those final conditions. So the same thing, we have our kinetic energy here, we have our gravitational potential energy, and we have our spring potential energy. There's still no spring. We don't even really need to worry about that. Okay, so there's still no spring energy. We have lost all of our gravitational potential energy. Right now, that ball is right at y equals 0, or right above. It's enough that we can ignore any other gravitational potential there. So we have lost that gravitational potential energy. The gravitational potential energy that it had was converted into motion. So the ball is moving. So all of the energy that was associated with the gravitational potential energy has been converted into kinetic energy. So all of it becomes kinetic. So this is our initial situation. We have this ball sitting up on the top. This is gravitational potential energy. This is our final situation where we have the ball just barely above the ground, and all of that potential energy has been converted into kinetic energy. Now, this is of course ignoring air resistance. We could over here have that dissipative energy, okay, where we have lost some due to friction. But for the most part, in a situation like this, we would ignore air resistance unless we have been told otherwise. So we don't have any of this. So this is that conservation of energy. We start out with a certain amount of gravitational potential energy. All of that is converted into kinetic energy as the ball has fallen down. So this just gives us a really nice visual of the transfer of energy within our system. From here, we can write a conservation equation. So we can describe this transfer of energy as an equation now. So what happens here, the potential energy that we had from gravity in our initial conditions is equal to the kinetic energy because our ball is moving. So instead of writing out that whole great big long thing that they have in their book, all you need is the gravitational potential energy before the ball started falling is equal to the kinetic energy of the ball right before it hits the ground. Now we know the equations for this. We've derived these from our labs and from other things. So we can actually say, if we know some other things, if we know the mass, we know how high this is, we can quantify this even more. We could substitute in that mgh, right? Mass times the gravitational constant times the height is equal to potential energy for the gravitation. Kinetic energy is 1/2 mv squared. This is kind of interesting because what happens here, mass doesn't matter. We kind of talked about that when we talked about forces, right? So when we sketch this out, this just gives you a way to visualize that. Especially if you're really not an equation person, which I am not. These are very helpful in order to kind of see what is going on within your system.